Hi all, welcome to the fifth video in this series. This video will demonstrate the use of radial basis function neural network for pattern identification. This video is made as part of assignment 5 of Nature Inspired Computing course at IIT Gandhinagar. 3 sets of key cards with security patterns are given to 3 persons. Person A has 3 cards, while person B and C have 2 cards each. To unlock the lock, first A has to insert any 2 of his 3 cards, then B has to insert any one of his or her 2 cards, and finally C has to insert any one of his or her 2 cards. The cards have to be inserted in the order A before B before C. We need to design a neural network that can unlock the lock using the aforementioned logic. To simplify the problem, we have converted the cards into decimal numbers using the following scheme. The positional values of the pattern on the cards are first converted into a 8-bit binary and then to its corresponding decimal. Hence, we can represent any card pattern with a unique integer in the closed interval 0 to 225. Therefore, we will have 3p2 permutations in which A can insert his or her cards and 2p1 permutations each in which B and C each can insert their cards. In total, there are 24 unlocking permutations, while the number of permutations which are possible is 256 to the power 4, which is huge, approximately of the order of 10 to the power 9. To use a manageable number of RBFs, we will need to cluster the unlocking combinations. We have used hierarchical clustering where we can easily cluster according to our requirement of number of clusters. This is the dendrogram drawn by the clustering algorithm. To get, for example, 4 clusters, we set a threshold around 95 and choose the clusters below that. To increase the number of clusters, say to 12, we simply decrease the threshold level to 40. For each cluster, we have a radial basis function. The function maps the input, a 4D vector space of combinations, to a Gaussian distribution. The parameters of the RBF are the mean and standard deviation for the Gaussian distribution. Now we come to the structure of the neural network. Say we use 4 RBFs in the network. Thus, the 4D input is fed to the RBF layer that gives a 4D output. This output is added after multiplying with weights and compared to a bias before passing through a symmetrical hard limit function. The output is a binary, true or false, corresponding to whether the lock unlocks or not. For training the neural network, we have used the 24 unlock combinations that should return a high output. The parameters of the RBFs are set from mean and maximum distance between 2 vectors in the cluster. We have determined weights matrix from the matrix equation w.phi equals y. Here phi is the 4D outputs from RBF layer for all the input unlock combinations stored column-wise in a matrix, and y is the expected output for the unlock combinations, which is an array of ones. Since phi is not always a square matrix, we take the pseudo-inverse to determine the weights. The bias for the hard limit function is determined by the minimum of summer output for the 24 unlock combinations. We tested the trained network using 10 million random combinations from the space of all possible combinations. Using 4 RBFs, the network accurately predicted the lock-unlock output 98% of the times. Though this is close to 100%, even with a 2% error, we may have 20 million combinations where the network incorrectly unlocks. Increasing the number of RBFs to 12, we see the prediction accuracy raises to very close to 1. Even though this corresponds to 4000 incorrectly identified unlocking combinations, this network lays the groundwork for even more complex logics for more secure locks. Thanks again and have a nice day.